So when you look at a cup, how do you know it's a cup? We're going to talk about object perception today. Your brain does these things that we've been talking about that make it seem as though perception is this completely obvious process and it's really simple to do, right? You can look at a cup and you say, oh, that's a red cup. I know what that is. I've known what that was since I was 3 years old. But how does your brain do it? How do you perceive objects? Anne Treisman spent her entire career looking at how the brain determines what things are, just by looking at them. She won the National Medal of Science, was awarded by President Obama, and basically she said that object recognition is a two-stage process. Her theory of feature integration kind of explains it in a very well and very thorough way. So the first stage she called a pre-attentive process, where there are primitives of the object, and her second stage was a focused attention stage, where these primitives are assembled or put together as an object. So essentially the visual system is taking apart the object and then putting it back together. Why would that happen? Well, first of all, let's talk about some of the evidence that shows that it does happen. What are primitives? According to Treisman, primitives are these building blocks of perception. And of course, if you have any good theory, new theory, you have to like make up some words, right? So people don't know what they are. They say, oh, that's cool, you've just made up some new words. So her new word was a texton. And essentially, a texton is a characteristic or feature of an object, right? So down here we have what we would say is a bicycle, but it's got all these shapes to it. So each of these different shapes can be a primitive or a texton. Color can be a texton, a building block of perception. So in the first part of her theory, she said primitives are identified in a really pre-attentive process that's outside of our awareness, right? So primitives are identified in a way that Thank you. So in the first stage of her theory, primitives are identified in a pre-attentive process that's outside of our awareness. In the next stage, the primitives are combined in a more focused attention stage, right? So now the stuff has come into our awareness and we're putting the parts together to form an object. And this is what we do next. We perceive a three-dimensional object that's in our world. We compare the object to memory. Is this something I've seen before? Oh yeah, it's a red cup. I know what that is. And if so, then we match and we identify it. If it's something you've never seen before, you're still going to have a three-dimensional image of it, but you're not going to know what it is. So here's some examples of feature integration theory. So I'm going to show you a quick display here, and your task is to just identify where the O is in this display. Ready? All right. Probably got that pretty quickly, right? Now I'm going to ask you to find where the R is in this display. Here we go. It takes longer to find the R, right? The second task takes longer because R and P and Q have common primitives. If we look at our display again, the R is right here, right? But it's got this little slant down here that the Q also has. It's got the kind of curved part at the top that the P also has, and it's got the the vertical line that the P also have. So they share more primitives. The curvature, tilt, color, line ends, movement, all of these things in Treisman's theory of feature integration can be primitives or textons. They're extracted from the display at the pre-attentive stage, and then they exist independently of each other. Don't believe it? All right, let's try this. I'm going to show you a quick display here. Your job is simply to write down what you see. Ready? Here we go. It wasn't that quick. Ready? Here we go. All right. Write down what you saw. Be very descriptive. So if you got it, you might say XST, which was the correct letters. But I'm going to ask you now, what color were each of those letters? And when we do this in a live classroom, we get, oh, red, green, blue. The X was blue and the T was green. And we get all kinds of different interpretations that you get, right? So the actual stimulus was a blue X, a red S, and a green T. But people report applying the wrong color to the wrong letter all the time. She called these illusory conjunctions. Her evidence that shape and color are separated and then they get put back together in the visual system. Illusory conjunctions. Sometimes the system makes errors and they get put back together incorrectly. So in the pre-attentive stage, the primitives are free-floating. Shape and color are not together, right? And movement are also separate. And it turns out that this is exactly how the visual system is designed or has evolved. We know that there are different visual pathways that process color and movement or shape. And so in a sense, the information is separated and then comes back together in the visual cortex, just like Treisman suggested. So combining the primitives at a location is important. The focused attention stage requires a location for you to focus your attention. The strengths of feature integration theory are that it parallels the physiology. The temporal pathway is also referred to as the what pathway. The parietal pathway is referred to as the where, the pathway. Attention glues these features together at a location. A very important object that we perceive every day are faces. And just like when we talked about motion perception, how biological motion is special, the perception of biological organisms and particularly the perception of faces is really, really special and different from other objects. So for example, if you turn other objects upside down, you don't have a big effect, right? So let me show you a face here and you tell me who it is. All right, how long did that take you? I can guarantee you that if I'd have shown it this way, you would have been able to recognize Greta Thunberg much more quickly. On the other hand, if we showed a house upside down, then it wouldn't really have that much of a detrimental effect. There wouldn't be this dramatic difference in recognition. All right, let's do another one here. Who's that? All right, so if you know Drake, you know that he's more easily recognized when he's right side up than when he's upside down. And the process that we're talking about here is that faces are perceived holistically. The relationship between the parts is important, right? So when we look at a face, we expect to have two eyes, above a nose, above a mouth. That configuration is important in identifying individuals. We can use it. We can rely on it. It's different from objects that don't have a kind of typical orientation, right? So for example, a house, you know, you could have the door in the middle and some windows in each side. You could have all windows over here and a door over here. There's no typical configuration for looking at a house. And so we don't get these dramatic effects of configural processing. So configural versus analytic processing. When we're looking at faces that are upright, we do analytical processing, right? We look at the nose and the eyes and the mouth. Just like we do a house, we look at the door and the windows and etc. But we use also configural processing, the relationship between where the parts of the face are to help us process faces quickly and automatically. We are experts at processing faces. Now, turns out that you can become an expert at processing other things if you have a lot of practice at it, right? So there are people who have these same advantages in processing types of dogs, right? So if you're a champion dog breeder, or if you're a car enthusiast, right? We can develop the expertise for these types of things, and we'll talk much more about this when we talk about face perception further on. I'm happy to hear your questions. Hope you're doing well.